Well, here, let me get it recording. All right, there we go. So as far as recording is concerned, I did try to upload all the other recordings that I have for previous classes, and YouTube was saying that there was an error with uploading. So unfortunately, I wasn't able to do it last night. I tried getting the videos going, and it just kept giving me an error. I tried, at two different points of the night, and both times, it flew a flag at me. So I'll try again today. Hopefully I can get those up for you, so that way you have over the weekend to review back any of the classes that you might have missed. And yeah, because I want to make sure that those are up just for the sake of it, in case anybody needs to review that as well as the actual lectures themselves. Okay, so number 6. Let's look at number 6 of the project packet together, and then we'll jump into questions from the review sheet. Okay, so for number 6, we are given a certain function, and it's a very weird function. So we're given f of x is equal to 1 over the square root of negative x. This is the first function that we're given. And what we have to do in part A is part A just says find the domain of the function, which basically just says find the domain of this fraction. So we look at this, and before we continue, well, if it says find the domain, that means that, again, your 3 rules should be popping into your head, right? Okay, I'm going to call on some people. Again, we have 3 rules for domain. We should list those rules, right? So let's see what we can do. Luke, can you list me 1 rule for domain? It doesn't necessarily have to apply here. I'm just looking for any of the 3.
Do we have to get rid of the negative x under the square root?
Okay, so what you're getting at here, we can't have a negative underneath of a square root. If we end up with a negative underneath of a square root, it's undefined, right? We can't have that. So no negatives under even powered roots. Otherwise, we have an issue. So okay, that's our first rule. What else can we do here? What's our second rule? Jacob, what's the second rule that, again, may not apply directly here, but is a rule of domain? Okay, I think actually last time I called on you, Jacob, you said your mic was broken. I'm not sure if that has been resolved or not, so we can move on. Brooke, if you can list a second domain restriction that we learned in this class.
That there can't be a negative under a radical.
Oh, well, that's the one that Luke just said. So should be 2 more.
That you can't have a radical in the bottom.
Well, we can absolutely have a radical in the bottom. 1 over square root of 1. Well, that should simplify to just give us 1, right? Square root of 1 is just 1. So you're getting closer, though. It does have to do with the bottom of a fraction. Let's see who just put their hand up. Kayla, yeah, help me out.
There can't be, it can't be equal to 0.
Yeah, your denominator can't come out to be 0, right? And that's just combining what Brooke was getting at and what you just said. You can't have 0 in your denominator, right? Because if you have 0 in your denominator, in this case, you would have 1 over 0, right? And then that would end up being undefined, right? You can't divide by 0. So cool, we have 2 rules. And then the last one, the one that doesn't apply to this question, has to do with logarithms. And it just says that the value in a logarithm has to be positive, exclusively positive, not 0. Okay, so for this one, again, we just talked about the 2 rules that apply. We have a square root, and we have to make sure that the value underneath it does not come out to be negative. And also, it's in the denominator, so we have to make sure that we don't get 0. So the way that we find the domain of this is we set up an inequality, because if it can't be negative and it can't be 0, we're looking for all of the positive solutions, right? We're looking for all of the numbers that make the denominator positive. So the way that we set up this inequality is we take everything that's underneath the square root, so in this case, negative x, and we set it to be greater than 0. So negative x is greater than 0. And then we proceed to solve. Now, normally, if hypothetically we had a different fraction where we had this exact same piece, the square root of negative x, and say it was in the top of a fraction, let's say we had this instead, square root of negative x over 3, the inequality we set up would be very, very similar. The only difference is that 0 would be okay to get, right? Because if we get 0 underneath of a square root, you would have square root of 0, which comes out to be 0, and then you would have 0 in your numerator, which just makes the fraction 0. So getting a 0 would actually be okay in that case. But notice that it's not okay in, for our actual function, f of x, because, we would, again, get it in the denominator, and that's a problem, okay? So we set up this inequality. So we have negative x is greater than 0. If somebody can help me out, how do I just clear this? What's the process for just solving for x in this case? It's just one step. Yeah, Shelby, if you can help me out. I saw you unmute yourself.
Divide by a -1.
Divide by -1. Great. So if I divide both sides by a -1, we're going to get x. We're going to get 0. What happens to my sign when I divide by a negative?
It flips.
Perfect. So now negative x is greater than 0. We have x is less than 0. So what that tells us then is that the domain of this function is all negative numbers. What that's saying is that if we write it in interval notation, like the directions said at the top of the project packet, again, we're looking for interval notations whenever you're writing domain. So this is from -infinity to 0, right? That's what x is less than 0 means. It means all the negative numbers up to 0. So what this tells you is that you can plug in any negative number in for x because there's already one negative underneath the square root. So if you plugged in, let's say, just hypothetically, I always use this number, if you plugged in -17 for x, for example, then you would have negative, because there was already one negative existing there, and then -17 for x. And now notice how the two negatives would cancel out, and you'd just be left with 1 over the square root of 17, and I don't care about tallying that. It doesn't necessarily matter. The point that I'm getting at here is that notice that you get a real number back. This is an acceptable thing to get back. You're not going to be dividing by, or you're not going to have a negative underneath of the square root. And the main reason for that is that, you're having the two negatives cancel out. So that's always going to happen regardless what negative number you plug in. Basically, again, is another way of saying all negative numbers are going to work. So part A, that's your domain. Okay, part B says find f composed with itself. Again, one more time, and I know that I put a function composition and a function combination question on the review sheet, so really take your time with it because there was a little bit of confusion on the project packet in regards to this. Just one more time, f composed with itself, or f composed with any function for that matter, does not mean f of x times f of x. These are two very different concepts. F of x times f of x, well, this piece right here would be f of x quantity squared, right? That's not at all what a function composition is trying to get at here. Function composition says one function becomes the input for another function. So what is that going to look like in this case? Well, in this case, again, if we have function composition, that means we're going to have an inner function and an outer function. And, well, since they're both f, it doesn't matter. You can write it as just f of x, right? And the way that you know which one is the outer function and the inner function is, again, you read it from left to right, where left is always going to be your outermost function. Okay, so we actually know what f of x is, though, right? Because f of x was given to us. It's this fraction. So with that being said, we can go ahead and say, okay, well, we have f of that fraction, right? 1 over the square root of -x. So now what this is saying is that this fraction is my new input for f. Instead of it being f of x, it's f of 1 over the square root of -x. What that tells us is when we go back and when we look at this fraction here, and I'm just going to erase the circle here just to make it a little cleaner. When we look at this fraction, what we're doing is we're inputting our new value in for x. Notice how we're not going to change anything else. The numerator is still going to be 1. It's still going to be a fraction, so we're still going to keep this division sign. The square root and the negative sign that it's already there, we're going to keep, okay? The only thing that we're going to do is we're just going to be plugging in our new fraction for x. So what this is going to look like is, again, we're going to keep everything that's essentially not the x. So to keep everything that's not the x means, well, we're just going to 1 over the square root of negative, right? Notice when I'm pulling this, I'm just extracting the same pieces that are just from my original function f, right? So 1 over the square root of negative, but instead of it being x, it's now this fraction, this piece right in here, because this is now my new input. So I have my new input, which is the fraction of 1 over the square root of negative x. And that's it. You didn't have to rationalize it. If you did rationalize it, rationalizing can help you. In particular, you would have had to do it twice. You would have had to rationalize first the outer square root, and then you would have had to rationalize the inner square root as well. But if you did do that, that's okay. And, again, that might help you for your understanding of Part C. But as long as you just gave me this, you didn't have to rationalize at all, and I accepted this as an answer. Okay? So again, notice what's not changing, right? Again, the 1 over the square root part and this negative, that's all just being pulled from the fact that this is function f, right? And the only thing that did change is this circled piece right here used to just be an x. But instead of it being an x, now it's the new input, 1 over the square root of negative x. Any questions on this part in particular before we move on to Part C? I knew this one would throw some people for a loop, so
I just want to clarify like that, right? How you plugged in the x, that is the function of f composed of itself, right?
Yes. Yep. This is all for f of x. So that's all this piece.
Thank you.
Yep. So this is all for part B, just finding f composed with itself. Correct. Okay. Okay, so we end up with this fraction, which is 1 over the square root of negative 1 over the square root of negative x. Okay, so part C now says, show or explain that the domain of this composition is no real numbers. There's actually a couple different ways that you can go about doing this. If you did all of the math behind it, what you're going to end up showing is basically you first care about this domain here. That's why part A is having you find the domain of f of x. Because when you're finding the domain of a composition, so that's what this is. Again, this is a function composition. When you're finding the domain of a composition, you not only care about the domain of the final result, so you don't just care about the domain of this piece, you also care about the domain of the inner function as well. And remember, the domain of the inner function, well, that's f of x, and that's what you found in part A. So what you have to do is you find the domain now of the total, and then you compare it to the domain of your inner function. If you guys remember going way back, what we did was we found the two domains, we put it on a number line, right? And then, we put like the two different colors. Maybe, this is for the inner function, maybe this over here is for the composition, and then only the parts where they agree would, be your final domain. You compare them, you exclude all the parts where they disagree, only the parts where they agree is going to be your final answer. So that's exactly what you have to do here. You just have to find the domain of this piece. So finding the domain of that and then comparing it to the domain in part A, well, this isn't really that bad. The reason it's not that bad is, again, you're just following the same procedure. So our procedure before in part A was, okay, well, again, we looked at this fraction and we said, okay, we're going to extract this negative x, the piece that's underneath the square root, and we're going to set it to be greater than 0. And we set it to be greater than 0 because, again, we had the two rules, right? You couldn't have 0 in your denominator. Also wanted to make sure that you didn't end up with a negative underneath the square root. So what we're going to do is exactly the same thing. We have this big square root, so we're going to take all of this stuff underneath the big square root, and set it to be greater than 0 for the exact same reasons. We don't want it to end up being, 0 in the denominator, and we also want to make sure that it comes out to be positive. So what we do is we say, okay, we have negative 1 over the square root of negative x is greater than 0. And now just start playing with this, right? Well, we see that we have this negative sign, so we want to get rid of that. So take it step by step. Start, just doing things that simplify this down. So we have this negative sign. I want to get rid of it. So I'm going to multiply both sides by a negative 1, or divide both sides by a negative 1, however you want to think about it. So we end up with 1 over the square root of negative x is now less than 0. Right? Whenever I multiply or divide by a negative, we flip the sign, and dividing by a negative number isn't going to change the fact that it's 0. So we have 1 over the square root of negative x is less than 0. I want to get rid of the square root now. So what I'm going to do is I'm going to square both sides, because again, notice how I have 0 on the other side, and squaring both sides isn't going to really do anything to 0. So when I square both sides, I'm going to end up with 1 over negative x is less than 0. And now one more time, I have this negative. So just to really finish simplifying things, I'm going to multiply both sides by a negative 1 more time here. And so I'm going to end up with 1 over x is greater than 0. Okay, well, if you guys remember from question 3 on the packet that had to do with rational expressions with an inequality, and you had to do test points, this is essentially the same thing, but just a much, 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 much simpler version of it. So all you're doing is you're saying, okay, well, we put a little number line here, and we say, all right, we know that we can't have 0, so 0 is going to be excluded, because, again, you would set x to be equal to 0, and that's when your fraction would break, right? So we can't have 0, so we're just testing these two intervals to see when this inequality is true. So when you test them, you find out that, of course, the only part that does end up being true is this side over here. And if you plugged in any negative number for x, you would find that obviously the inequality is not true, right? If you plugged in negative 1, for example, you would have 1 over negative 1, which simplifies to be just negative 1. And negative 1 is, of course, not greater than 0. And this is the case for plugging in any sort of negative number. So great. So when you find the domain of our function composition here, we find this domain to be positive numbers. So from 0 to infinity. And then again, the last thing you have to do is compare it to the domain of the inner function, which you found in part A already. So comparing it to the domain in part A, just going to draw my number line. We don't have 0 in either of the cases, so 0 is excluded. And I'm going to draw the domain from part A in red. So that's, of course, going to be this piece over here. And we found that to be all the negative numbers. So that's all these guys over here. And then for part C, when we started, going down this path and figuring out all of this business, we found it to be the positive numbers, right? So all the positive numbers, or all the numbers that are bigger than 0. So that's going to be all of these. And now remember what I said. What you're doing is you're just comparing them and seeing where they agree. So your final answer is going to be all the points where they agree. But in this case, there are no points where they agree. Notice how there's at no point the red and the blue ever touch each other, right? The only point that they might have had in common was 0, but you can't have 0, and we showed that in both cases. Right? 0 doesn't work over here when we were talking about just the domain of the original function, and 0 also still doesn't work when we're talking about the domain of the composition, right? If you tried plugging in 0, notice how it still breaks. You would have 1 over 0. So you end up finding that there is absolutely no point where this works, and so we validated the, what it says for part C, which is explain that the domain is no real numbers. So your final domain is no real numbers. Again, there's a couple different approaches. That is doing all of the math, every single step, precisely, doing everything that you can to be rigorous and showing that there's not a single number where this works. However, there's other ways that you could think about it. So if you saw what was going on immediately, the way that you could think about it is you could notice, and I'm just going to erase a lot of this stuff just so I have room to write here. Okay, so if you saw what was going on after you did your composition, you would notice that what you found in part A was that x had to be negative, right? Part A says for your inner function to work, x has to be negative. So when you do your combination, or I'm sorry, your composition here, you know x has to be a negative number. So you're plugging in x here. And when you plug in any negative number, that's going to make this entire fraction positive, right? Because if you plug in a negative number here, the two negatives are going to cancel out. And then, of course, you're going to have 1 over the square root of a positive number. However, you have this negative sign hanging around here. So it doesn't matter what positive number your fraction comes out to be. You're always going to have a negative of a positive, which means you're going to have a negative number. And so you're always going to end up with a negative underneath of a square root, regardless what value you plug in for x. So that was one explanation that I would have totally accepted. A couple of you actually found that and wrote that down, and that was something that I was totally fine with. You didn't have to do all the math as long as you figured out that, oh yeah, your fraction here is always going to be positive. You're always going to have this negative, so you're going to have a negative times a positive underneath of a square root, which means your total value is negative underneath of a square root, which means it's never going to work out. So regardless how you went about it, and again, there was a third way that involves rationalization, which takes a little while, and I'm not gonna go through because it's a little bit convoluted. But if you did that way as well, I accepted it, and that was fine. So does anybody have any questions on this one? Again, I know this was really tricky, but that was the whole point of it. This was a very difficult one, but that's why this is a semester-long project. So if you have questions on this, please let me know. Okay, cool. So let's go ahead and look at the review sheet then. That was the only thing from the project packet that I didn't really have time for before that I absolutely wanted to do. So moving over to the review sheet here. Whoops. There we go. There is a couple problems in particular that I find to be really, really useful to go over, especially given how the project packet went and common mistakes that I saw in the project packet. Domain still seems to be something that, some people are struggling with. So if you're struggling with domain, I put 3 different domain questions on this review sheet. Because it should give you a decent amount of practice. The domain questions are number 6, number 12, and part D of number 13. I want to go through number 12 together just so we can see the concepts in action and see how you would handle finding the domain when there's a bunch of different pieces and a bunch of different rules being broken. So we're going to go through number 12 together, but if you have questions on the other domain questions, either email me or save them for Monday, because again, going into Monday, that's all you guys. I'm not going to come in with anything prepared for Monday. That's entirely your time to ask your questions. Okay, so let's look at number 12 from the review sheet. Number 12 is we're trying to find the domain of function f. So f of x. So we have f of x is equal to the square root of 3 minus x over x minus 2 plus the natural log of x minus 1. Okay, so with all of this going on, it might seem a little daunting to try to find the final domain of your function, but split it into parts. The best thing that you can do here is realize that there's only ever 3 rules that your domain could break, right? We talked about them in the last, when we were talking about the question 6 of the project packet. So just to reiterate, your 3 rules here: if you have a fraction, your denominator can't be 0. If you have an even-powered root, you can't have a negative sign underneath of an even-powered root. And finally, if you have a logarithm, even if it's a natural log, if you have a logarithm, the value of that logarithm has to be positive only. So that means this x minus 1 here has to come out to be positive. So what we're going to do, given all of that, well, we see, okay, well, there's a fraction. We have our variable in the denominator of our fraction. So yeah, this x minus 2 is probably going to break that rule regarding not having a 0 in the denominator. we have a square root and we have our variable underneath of the square root. So we have to check and make sure that this, we have to find the domain of this piece as well, because finding the domain of that, of course, means we have to exclude the negative possibilities there. And lastly, we see that we have a logarithm. So all three of our rules here we have to go through. And this is why number 12 is, kind of a doozy, but, one that we're going to work through here together. So the way that we approach this is we split it into parts. Let's first tackle the x minus 2. So I'm just going to rewrite everything, but I'm going to color code things so that way we can keep track of what's going on. So we have the square root of 3 minus x in red. Then we're going to have this x minus 2 in blue. And finally, the logarithm piece, I'm going to put in green. And so this will, help you keep track of what we're doing. So we're going to tackle the blue piece first, the x minus 2. So how do we figure out when the denominator is 0? What do we do here? If we're trying to find out when it's 0, there's only going to be one or, a specific number of points that make it 0. So how do I do this? How do I find when x minus 2 is 0? What's my process? Yeah, Keji, we're going to set our denominator to equal 0. So we're going to take our x minus 2 and set it equivalent to 0. So that way we can find the particular point or points that make it 0. So we have x minus 2 is equal to 0. Okay, so now we're just going to go ahead and solve. Solving this isn't too bad, right? So we have x is equal to 2 just by adding 2 on both sides. What this tells you is that at x is equal to 2, so if you plugged a 2 in for x, you would have 2 minus 2, which simplifies to be 0 in your denominator, and then the fraction falls apart, right? So that 2 tells you that you can't have it. You just absolutely cannot have that point. That is the problem child right there, right? We can't have it. So we know that in our final domain, we're going to be excluding 2. If you want to go ahead and write the intervals along the way to help you keep track, that's okay. So the interval for this piece would be all real numbers except for 2. So that's all the numbers to the left of 2, union with all the numbers to the right of 2. You don't have to write the interval at each step because, again, we're going to be combining them in the end. But again, if it helps you keep track, then go for it. Just make sure if you're doing that on your test, you're not circling this, because circling this indicates this is your final answer. Okay, so now let's do the piece in red. So the piece in red is going to be the square root of 3 minus x, right? So for this here, again, our rule says we can't have a negative number. But let me ask you, can we get a 0? Is it okay to have a 0 in the numerator? So if we get a 0 underneath the square root, is that okay? Yes, no, maybe. Yes, it is absolutely okay. So what that tells us is when we set up this inequality that we're about to set up, we know that one of our solutions could potentially be 0. Whether we set it up as greater than or equal to 0 or less than or equal to 0, we know that it could possibly equal 0. So we just have to make sure we're using the correct inequality here. So we know our process, and our process is we're taking the stuff that's underneath the square root and finding when it's negative, right? So we're going to say, okay, 3 minus x, that's the stuff that's underneath the square root. And what we're going to do is we're going to set it to be greater than or equal to 0. The reason is, again, if we set it to be greater than or equal to 0, we're guaranteeing that when we solve for x here, we're getting positive solutions. We're getting only the positive numbers back for, when we plug in x underneath that square root, or 0 in this case. And that's why we have this, greater than or equal to. So solving this isn't too bad. All we're going to do is we're just going to add x to both sides, right? And the roundabout way is you could subtract 3 and then multiply both sides by the -1. Just remember to flip the sign if you do that. But the straightforward way is just adding x to both sides. So we're going to have 3 is greater than or equal to x. And of course, you can just rewrite that as x is less than or equal to 3. So what this tells you is, again, if we're writing our intervals along the way, this is saying x could be 3 or x could be any number that is less than 3, and that's going to make your piece in red okay. So writing this in interval notation, that's all the negative numbers and all the numbers all the way up until 3, bracket at 3, because 3 is, included. If we have x is equal to 3 in our square root here, then we would have 3 minus 3 underneath the square root, which would give you square root of 0, and you absolutely can have 0 in your numerator, so that's okay. All right, so the last thing we have to do here before we start combining our intervals, before we start combining things, is we just going on with this natural log. Now remember what I said, it doesn't matter if it's a natural log or a regular logarithm, the value has to end up being positive, and only positive. You can't end up with a 0. So what do you guys think we're going to do here to try to figure out, the positive solutions? It's going to be very similar to what we just did with the square root, with just one very small difference. I don't want to call on anybody in particular for this one, so if anybody wants to, just shout out an answer. X minus 1 is greater than 0. Exactly. Perfect, Aline. So x minus 1 is greater than 0. What we're doing is we're extracting the value of the logarithm, so in this case, the x minus 1, and because we want it to be positive, we're setting it to be bigger than 0. Exclusively bigger. You're not making it greater than or equal to, because if you do that, then there's one particular point that would make it equal 0, and we don't want a 0. Remember, the domain of a logarithm is only positive. Okay, so x minus 1 is greater than 0. Solving for this isn't too bad, right? Just add 1 to both sides. So you get x is greater than 1. And writing this in interval notation one more time, if you're, doing that sort of thing, then that means you're starting from 1, you're not including 1, so parentheses here, and you're going to infinity, right? All the numbers that are bigger than 1. So the last thing that you have to do here, we basically did all the hard parts. We just need to find a way to combine all these intervals together and see what our final interval is going to come out to be. We have a whole bunch of restrictions going on, so let's just see what our final interval comes out to be. And the easiest way to do that is, at least for me, and hopefully, some of you guys also feel the same way, is visually. Visually, if we just put it on a number line, then it generally makes the most sense, right? So what I'm going to do is I'm going to draw a number line here. I know that I'm starting from 1 for the part in green. I know that there's something to do with x is equal to 2 for the part in blue, so I'm going to put a 2 down here. And I know that there's something to do with 3 for, this one over here. So that's why I'm putting 1, 2, and 3 on my number line here. So for the part in blue is saying that 2 is the only number that we can't have, right? 2, when x is equal to 2, we have a giant problem. But all the other numbers should work out. So I'm going to go ahead and just put an open circle here for 2. And I'm not going to, it's fine. We'll go ahead and put the blue. So the blue just says, yep, we can have all the other numbers other than 2. For the red piece, the red is saying, okay, well, starting from 3, we want all of the numbers to the left of 3 and including 3, right? So we're going to put a red closed circle here on 3, and we want all the numbers that are to the left of it, right? So all the numbers to the left. But now remember, we're excluding 2, right? So we can't possibly include 2 in our final domain, even though it's included for the piece in red. 2 is absolutely part of that interval, but when we're combining all of these restrictions, we see that, oh yeah, x is equal to 2 is still a restriction, so we can't have that. And the last piece here that we have to do is the part in green, right? So that's from 1 to infinity. So the part in green is an open circle here, and this is going from 1 to infinity. So all the way that way. So now we just have to say, okay, where is there green, red, and blue that, we can absolutely extract from this little messy diagram here that we have going on? Well, the piece to the left of 1, so all of this stuff, everything to the left of 1, notice how there's only red and blue, right? So there's no green, so obviously this part doesn't pan out. And we know that because, of course, there's nothing in this interval, there's nothing to the left of 1. So this piece to the left here, there's nothing over there, we're going to exclude that. If we're looking at the of 3, so all of this from, going from 3 to infinity, notice that there's no red here. And of course that should make sense because this interval stops at 3. So we're not going to be excluding anything on this side. Or, I'm sorry, we're not going to be including anything on that side. So the only things that we have to really worry about is the stuff in between. Whoops, let me go ahead and just erase this stuff. So, and when I say the stuff in between, I'm talking about the stuff in between 1 and 3. So this entire area here, right? So this entire area just says, okay, well, there's green, red, and blue. So we know that there's definitely going to be some solutions in here. We just have to be really careful about how we set this up, right? So we know we're starting from the number 1. So we're starting from 1, but we're not including 1, and we know that because, again, there's an open circle on it, right? So parentheses at 1. And then we want all the numbers. Notice how in this interval here, there's still green, red, and blue. So that means, we're good to go for all 3 of these intervals that we talked about. So from 1 to 2, we don't have a problem. At 2, remember our original restriction for the piece in blue here. At 2, we have a hole in the graph, right? So we can't possibly put 2 in our solution. So we just say from 1 to 2 is our first piece of the interval. And then it picks back up again after 2, right? So from 2 to 3, well, this is okay. So we go from 2 to 3, but between 1 and 3 is that we actually want to include 3 in our solution, right? 3 works for the red, it works for the blue, it works for the green. So we put a bracket here. So your final domain is from 1 to 2, union with 2 to 3. Again, the entire idea here is you set up, or you find your 3 different restrictions here, right? Our 3 restrictions were the square root. You didn't want negative numbers underneath of it. We didn't want a 0 in our denominator, and we wanted to make sure the value of our logarithm was positive. So we just tackled those one piece at a time. And then after we do that, it's just a matter of, combining all these different restrictions, maybe trying to use visual aids, but maybe you don't necessarily need it. If you can see, that this piece we're starting from, and when I say this piece, let me draw some arrows here. When the piece in green is starting from 1, and the piece in red is going up until 3, and the only restriction between 1 and 3 is this x is equal to 2, then it might be a little more intuitive for you to say, okay, well, it's going from 1 to 3, and it breaks at 2, so we can't include that, and you just have to worry about the 2 endpoints, 1 and 3, which you can, of course, figure out from your previous knowledge over here. Does anybody have questions on this one? This is, obviously a pretty tricky domain question, and I wouldn't put this on the test, but this is great review for domain for the exam. So if you have questions, now is a perfect time. You guys are all good with this? You're all happy with domain? You're telling me if I change all 10 of the questions on the final to be domain questions, you guys would be thrilled? Okay, cool. I'll take that into consideration then. All right, let's go ahead and clear this off, and let's move on to another question here. So that was domain. I'm not going to do another domain question today. It's already 11:40, so with the interest of time, we're just going to go to another question that I feel like a lot of people would benefit from. So that one is just, we'll get started on number 4. I don't know if we'll actually have time to finish it, but at the very least, we'll start looking at number 4. So the reason that I think number 4 is going to be good to look at is because we kind of breezed through that section a little bit. We definitely did examples of sketching functions together, but it's been a while. And I want to make sure that we still remember, end behavior, how to find intercepts, how to find, the test points to find the signs of your function in specific intervals, and then using all of that knowledge to be able to sketch your final graph, right? So our g of x here for number 4, it says we want to sketch the function g of x. So g of x is equal to x squared plus 7x plus 1. Okay, so this one isn't obviously the hardest polynomial for us to sketch because it's a quadratic, right? And for a fact that a quadratic is just going to end up being a parabola because anything with an x squared generally is just going to be a parabola. But, you could still follow the same steps anyway, and the same steps will lead you to be able to sketch any function in general. So to sketch this, first let's find the end behavior. Remember, there's only 4 different cases for end behavior, and it all has to do with the power that you have, whether it's an even power or an odd power, and the sign of your coefficient of your leading term. So when I say the sign, remember I'm just talking about positive or negative, and leading term or leading coefficient, that's just the coefficient of your highest power. So in this case, your leading term, or your leading coefficient is just a 1 or a positive 1. So because you know that it's a positive 1, and because you know that you have an even power, your end behavior, if you were to draw a graph, your end behavior is going to look something like this. Your graph at its final, when it starts going off to infinity, it's going to be pointing upwards for both of its arrows. It's going to be just going up to infinity. Again, the other situations that could occur if you have an even power. So this is if you have positive coefficient, even power, right? The other situations could be if you have a negative coefficient, but you still have an even power. So say this was like a negative x squared, for example. Well, all that's going to happen is that it's just going to flip the graph, right? So if we have a negative coefficient and an even power, then your graph would just be flipped, right? So that means that your end behavior of the graph would be your 2 arrows, both of them still now just pointing downwards. And then the last 2 are if you have, positive coefficient or negative coefficient of an odd power. And for that, what it tends to, regardless what the odd power is, it tends to x cubed, right? So what x cubed looks like for our end behavior is 1 arrow going upwards and 1 arrow going downwards, like this one. And again, this is for a positive coefficient with an odd power. And then if it were a negative coefficient with an odd power, then of course, again, it's just flipping the graph, right? So instead of your first arrow being pointed downwards, your first arrow is going to be pointed upwards. And then, of course, that means this one goes downwards. I have no idea what's happening in the middle of the graph, none whatsoever. But that's okay because we have other tools to figure that out, right? Just figuring out the end behavior is really useful because just knowing the leading term gives you that much information already. So in this case, again, because it's a positive coefficient and because it's an even power, we know that this one is what we're looking for. We know that this is going to be the end behavior of our graph, that when it tends to infinity, both parts of the graph are going to be looking upwards. Okay, so let me go ahead and clear some space here. And this was, if my memory serves correctly, this was from chapter 3 point something in your textbook, 3.1 or 3.2. I think 3.2 is more precise. So the lecture that corresponds with that is somewhere around lecture like 16. So just go back in the lectures if you have no idea what I'm talking about, and just try to look for, sketching a polynomial in the description of the video. I'm sure you'll find it. It's, not too difficult to find. I did detail or put little notes for each of the YouTube videos, so that way it corresponds with certain material that we've covered. So great. So we figured out the end behavior. So we know what, in the end, what the function should look like. Now we just have to figure out the middle pieces, and the middle pieces are determined by the intercepts and by the signs of your function for specific intervals. So okay, let's go ahead and find the intercepts. How do we find the y-intercept? What's our process for finding the y-intercept for a function?
Set x equal to 0.
Yeah, setting x equal to 0, right? If you're finding the y-intercept, you set the opposite variable to be equal to 0, and you just solve for y, right? But there currently is no y, right? But remember, we can freely go from function notation to the equation notation, so we can just substitute g of x for y. So instead of g of x is equal to, so on and so forth, it's now y is equal to x squared plus 7x plus 1. Okay, and now again, just like we established, we're going to go ahead and put zeros for x to find the y-intercept, right? So y-intercept means we're going to go ahead and put y is equal to 0 squared plus 7 times 0 plus 1. Well, notice the first two terms just drop out, right? Because they have x's in there, we're putting zeros. So y is equal to 1 is going to be your y-intercept. That's it. So when you're, if we're talking about what this actual looks like as a, as an ordered pair, remember that means that your opposite variable is always going to be 0, right? So x is going to be 0, and so your ordered pair looks like 0, 1. So great, we have 1 point of the graph already figured out. Fantastic. Let's go ahead and figure out the x-intercepts now. So if to find the y-intercept, you set x to be equal to 0. To find the x-intercepts, you're going to set y is equal to 0. So coming over here, we have doing the same exact process, but now y is equal to 0. So we have 0 is equal to x squared plus 7x plus 1. Okay, so for this one, how are we going to do this? Can we factor this? Is there anything that we can do to factor this? Probably not, right? Because we're working with a 7x for our middle piece, and we're working with a plus 1. So this doesn't really look like we can factor this. Okay, so if you can't factor it, what are some of our other options that we can do for solving quadratics? We learned a couple different things here. Yeah, quadratic formula. That's the one that probably jumps out to most of you, hopefully. Another option that we could do is we could try completing the square. And if you guys remember, completing the square is the process of using the tool b over 2 squared, and that's what you'd be adding and also taking away simultaneously. But we can just jump to the quadratic formula. So using the quadratic formula here, well, quadratic formula says x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Quadratic formula, that monster that we dealt with before. So if we're going to try to figure this out, we have to just plug in for b, for a, and for c, right? Well, remember what a, b, and c correlate to. Quadratics are in the form of ax squared plus bx plus c, right? So a is your coefficient of x squared, b is your coefficient of x, and c is your constant. So when we plug this all in, we're going to be having x is equal to negative b. Well, b is 7, so we're going to have negative 7 plus or minus the square root of b squared minus 4ac. So 7 squared minus 4 times a, which is 1, and c is also 1. So 4 times 1 times 1, all over 2 times a, which again is also 1. So I'm just going to leave that as 2. Okay, doing some simplifications here. X is equal to negative 7 plus or minus. We get 7 squared is 49. So we have 49 minus 4, right? And this is still all over 2. Simplifying again, square root of 49 minus 4 is square root of 45. All over 2. And we can actually reduce that square root of 45, right? Because what we're always looking for when we're trying to reduce a square root is we're just trying to, factor it so that we can get a perfect square out of it. And 9 seems like a perfect square, right? 9 times 5 factors of 45. So we can obviously simplify this to be negative 7 plus or minus 3 times the square root of 5 over 2. It doesn't look pretty. However, these are going to be your roots, or these are going to be your solutions for x, which means that you're going to have two different solutions, of course, because it's plus or minus. So your 2 points here are going to be negative 7 plus 3 square root of 5 over 2. Oops, all over 2. My mistake. Comma 0, right? Again, this is your x-intercept, so there shouldn't be any y component. And then your other one is going to be negative 7 minus 3 square root of 5 all over 2. Comma 0. So now you found your two x-intercepts. And plotting those might be a little bit tricky. Obviously you can use a calculator here to actually figure out what the approximate value is, so that way you know exactly where this is going on your x-axis. But at the very least, you now have your two x-intercepts. It's now 11:50, or actually 11:51, so I'm going to go ahead and stop here. But this is a good place to stop anyway, because you've now found all three of your intercepts, right? You found your two x-intercepts, you found your y-intercept, and you know your end behavior. So all you have left to do is, just figure out the direction of your graph, and that's it. Then you can now sketch it based on the 3 points that you figured out. Okay. So again, I'm going to go ahead and end the recording here. If anybody has any questions or anything on the review sheet, please feel free to reach out to me. And come Monday, come prepared with your questions. So over the weekend, take your time, try to study, figure out what you don't understand. So that way on Monday, you can ask it in class and we can go through it together. We're going to have one last office hours Monday afternoon as well, 4:15 to 5:15. And hopefully today I can try to get the rest of those YouTube videos uploaded. All right, guys. Thank you very much. Enjoy the rest of your day, and I will talk to you on Monday. Have a good one.
You too. Have a good weekend.